Hello and welcome to the theory prep video. This one's on the contrapositive, which is a new proof technique. So let's take a look at a problem that will sort of motivate our discovery of the contrapositive. First, we're going to start with a definition. A real number r is rational if it can be written as the ratio p over q for some p and q that are integers. The name rational comes from the fact that we can write it as a ratio. Otherwise, we say the number is irrational. And I think the best way to think about real numbers for now is they're just all the numbers on the number line. So like 0, 1, 2.5, includes things like pi, and the official or the theoretical, technical, mathematical definition is basically a unique set of numbers that are characterized by certain properties, but we don't really need that for now. So we'll just think of the real numbers like this. And we're going to try to prove a theorem, which is that if r is irrational, then the square root of r is irrational. So if you like take square roots and stuff, you sort of stay within the irrationals. And we have a little bit of trouble proving this because our definition gives us a good idea of what a rational number is, but it sort of defines the irrational numbers as like everything else. It doesn't really give us a property. It sort of defines it with respect to something else, and sort of hard to work with irrationals. We'd much rather be working with rational numbers, right? Because we know we can sort of write them a certain way, and we can work with some properties. We know some stuff about integers. So we'd be really excited if we could turn this statement about irrationals into a statement about rationals. So basically, if we could take p and q and negate them, then we'd be working with r is rational and square root of r is rational. So that would make the proof a lot easier, and that's going to motivate our study of the contrapositive today. So we're going to try and take proofs of implications and write them in a way that might be easier to prove. So in order to come up with the contrapositive, we're going to need to better understand what it means to prove an implication. Let's take an example here. For x an integer, if x is greater than 2, then the absolute value of x is greater than 2. So you can see this is a true implication. But what do we actually mean here, like mathematically? What we mean, we can rewrite this as for any integer, right, for any x and z, the following statement is true. And that statement is x greater than 2 implies the absolute value of x is greater than 2, right? That's what we're saying. We're saying for x an integer, so if x is any integer, then this parenthesized statement evaluates to true. And so what that means is that an implication is a binary operation. And by binary operation, I mean it's an operation on true or false, just like an AND gate or an OR gate, right? An AND takes in 2 bits that can either be true or false and returns true if and only if both of the input bits are true. Or an OR gate returns true if at least one of the bits is true. So in the same way, this implication takes 2 bits, right? First, it takes this x over 2 bit, right? And for some specific integer, x and z, x over 2 will either be true or false, right? If x is 3, then it'll be true. If x is like -4, it'll be false. And then it takes the second bit, which is either is the absolute value of x greater than 2, right? So for something like 5 or -5, it'll be true. For something like 0, it'll be false. So the implication operator takes in a p and a q and gives us a certain value. And we can actually write that out in a truth table, just like for and or you can define it by writing it out as a truth table. So the important thing here is that the binary operation summarizes our intuition, or the binary operation for implies summarizes our intuition for a rule that if p is true, then q is true. So let's go through the truth table. So if p is true and q is also true, well, is that consistent with our rule? Well, yes, it is, because our rule says if p is true, then q must also be true. And here p is true, but q is also true. So in that case, this is consistent with our rule. So our binary operation will return true. In the second row, if p is true but q is false, this does not agree with our rule, right? Because our rule says if p is true, then q must also be true, but here q is false, which contradicts our rule. So since it's not in agreement, our binary operation will return false. In the other cases, note that our rule says nothing about what should happen if p is false. It only says if p is true, certain things should happen. So if p is false, q can be anything that it wants to be, and it'll still be in agreement with our rule. So in those cases, we return true because it agrees with our rule regardless of what happens there. And so the consistency of this truth table with our intuition that P implies Q is exactly why we define this binary operation as P implies Q. So this suggests sort of another proof strategy, right? We wrote theorem 12 out like this, but in general, we can write a lot of implication statements as like for any S or for any N in, let's call it some set S, the following binary operation is true. And that binary operation is P of S implies Q of S, right? This is like usually what we mean when we say, like this implies that for everything in this set. And so then and just to relate this to theorem 12, right here, S in theorem 12, S is the set of integers. P of S is S greater than 2, and Q of S would be is the absolute value of S greater than 2. And so basically this helps us understand an implication as checking to make sure that a binary operation is always true over some elements of a set. And so the proof strategy here is, well, remember when we were working with reals and rationals, or rationals and irrationals, our problem was, we want to work with the negations of the statements. We don't want to work with P and Q. We want to work with not P and not Q. So if we could take this parenthesized statement and rewrite it in terms of not Q and not P, but just keep the exact same truth value in the parenthesized statement, right? So we write some other statement using not Q and not P, but that's true and false exactly in the same cases as our original parenthesized statement. Then our new statement is logically equivalent to the old one, so we can just prove the new one. So that might have been a little bit fast. So I have written out what I mean here, right? So in general, if we have some, for all integers, for all real numbers, this thing, this proposition implies this proposition. We usually write that, right, as for any n in S, P of n implies Q of n. And so if instead we replace the second part right here with another statement like not Q of n implies not P of n, if these two statements are true and false in exactly the same cases, then these two statements are logically equivalent. And so we can just prove the second one. So let's check to make sure that's true. So here again, I've just written out the truth table for P implies Q. I just copied that from the previous slide. And so now let's fill this in. So we have not Q. So not Q is false, right? Because Q is true. Not just flips the truth value. So here would be true, and false, and then true. And not P would be false, false, true, true. And then so now we can write the truth table for not Q implies not P, right? Just using the truth table for implies and using the values of not Q and not P. So if not Q is false and not P is also false, then not Q implies not P is true. Right? We can go back to our previous table, right? If the first input to implies is true, false, and the second input to implies is also false, then the value is true. Now, if the first input is true and the second input is false, well, then it evaluates to false, and you can check that the other ones will evaluate to true. So what we see here is that P implies Q and not Q implies not P have literally the same truth values. Like as a binary operation, they give the exact same values. So we can check if we're trying to prove that this binary operation always evaluates to true, well, we might as well just prove that this binary operation always evaluates to true, and that's the exact same thing. So that's what the contrapositive gives us. It allows us, instead of proving P implies Q, to prove not Q implies not P. Let's summarize this though, because it's been like a lot of truth tables, a lot of math, a little bit confusing. What is the key takeaway? The key takeaway is we now have a proof technique. Instead of proving P implies Q, we'll just prove not Q implies not P. And since those statements are logically identical, proving either is sufficient. And I also want to give a little bit more intuition about what a contrapositive is. I think it's a little bit easier, instead of thinking about like mathy stuff, is to think about just like sentences in English. And so one implication we could have in English is if it's raining, then my car won't start, right? Like maybe your car just like doesn't really work very well in the rain. If we take the contrapositive of that statement, then we negate my car won't start and we get my car starts. And then we negate it's raining and we get it isn't raining, right? So what this says is that these two statements are logically equivalent. They express the same sentiment. If it's raining, then my car won't start, or if my car starts, then it's raining. Those express the same logical relationships between variables. And so hopefully that helps you sort of see an example of it. So let's go back to our problem and see if we can apply the contrapositive. So this here is P, right? And this here is Q. So instead of proving our theorem, what we're going to prove is if square root of R is rational, right, because we negate Q, then R is rational. And this will be a much more palatable proof. So if square root of R is rational, then we can write square root of R as equal to P over Q for P and Q integers. And then that means that we can square both sides and we get R is equal to P squared over Q squared for P squared and Q squared in the integers. Because if you take an integer and you square it, you still get an integer. And that means, by definition, that R is rational, which is what we wanted to prove. So now we've proved the contrapositive, which we know is logically equivalent to the theorem. And so now we've proven the theorem. And this is much easier, right? So sometimes the contrapositive can be much easier to prove than the actual statement. So if you're ever having trouble proving the actual statement, maybe try writing out the contrapositive and see if you can prove that instead. That's really the end of the content for today, but I did want to answer one question that I think sometimes comes up, which is, how is this different from proof by contradiction, right? Because in the previous problem, we could have proceeded by proof by contradiction. So we would have said, assume R is irrational, and then suppose towards a contradiction, square root of R is rational. And then we would have concluded that R is rational, and then that would have been a contradiction. But the actual math that we did would have been the same thing. That's a good question. And to me, the concepts are highly intertwined, but they're a little bit different. So let's say in total generality, you're trying to prove P implies Q, right? So if you are doing proof by contradiction, then you assume P and not Q, and then you can conclude anything to contradict the statement, right? But often we conclude not P, and that will contradict P. But that highlights the first difference, which is that you could conclude something that just contradicts, some other thing, like the pigeonhole principle or something that you know about integers or something like that. So that's one difference. It makes contradiction a little bit more of a general technique. And then if we're proceeding by the contrapositive, then we assume not Q, and then we conclude not P. So here we're not assuming P, which is a slight difference as well. I think a big difference is that proof by contradiction you can apply it a lot more places. Like a contrapositive, you can only apply it when you have this implication, right? That's where we get this structure from. But you could prove by contradiction, for example, that there's no largest even integer, because if you suppose that you have the largest even integer, we'll add 2 to it and you get an even larger one. So you can prove other things that aren't necessarily implications by proof by contradiction. So sometimes it's a little bit more powerful. The last thing that I want to say too is that it's a contrapositive provides sort of a clean, nice logical formula that you can reuse to rewrite implications. So sometimes that's convenient. Whereas a proof by contradiction doesn't really give you that. And lastly, I think that hopefully seeing the truth table and that type of analysis for the contrapositive also helps you gain a little bit more intuition by proof by contradiction. So in that way, it's nice that they're related.